and good evening to all delegates from around the globe. I would also like to take the opportunity to thank the organizers for the invitation to give today's talk. In contrast to previous talks, my talk will be a short review on scanning probe microscopy in food science and is not an active research currently in my department. My background is experimental condensed matter physics, working with scanning probe microscopy since 1996, applied to nanostructures combined with light sources like laser or synchrotron radiation. Food, from the perspective of a physicist, can be considered as soft matter, with building blocks and processes occurring at the nanoscale or sub-microscale. Therefore, the idea of combining scanning probe microscopy with food science led to today's talk. It is interesting that although scanning probe microscopy has been invented in 1986 by Bynum and Rocher, up to date there are very few applications in food science. As a start, scanning probe microscopy refers to image formation of surfaces using a probe that is rastered across a specimen. If the probe senses an atomic force, then the technique is atomic force microscopy. If the probe is sensing a tunneling current, the technique is called scanning tunneling microscopy. If the probe is an electron beam, the technique is called scanning electron microscopy. And besides these three main categories, there are other variations. Focusing on atomic force microscopy, the working principle is a cantilever. At the end of which there is a tip, which is scanned across the sample surface, while trying to keep the force between sample and probe constant. If we focus more on the setup, we can see the sample, the tip, about size of nanometer, a cantilever sprig, and a sensing mechanism which composes of laser diode and a photo position-sensitive photo detector. The detection of tip-sample force interaction is through a cantilever bending following Hooke's law. In terms of physics, the force can be either in the attractive regime or in the repulsive regime. In the repulsive regime, we have the AFM operating in contact mode, whereas in the attractive regime, we have the tip, the AFM operating in the non-contact mode. Between the two, there is the tapping mode, where the tip just touches the sample very lightly. At the inset at the bottom, you can see as the tip is moving across the sample's surface, the piezoelectronics tries to adjust the distance between the tip and the sample in order to keep the force constant. A review 2 years ago by a team of Obeid and Geomar addressed the importance of AFM in food science. In particular, AFM can achieve nanometer detail in biological samples, thus allow observation of live objects at the molecular level. The samples can be seen in ambient or liquid environments, therefore at relevant conditions for biological samples, for example, at various temperatures, various pH, etc. It can be used to image dynamic events for molecular mapping. However, as I said at the beginning of my talk, growth of AFM in food science is very slow. For instance, a simple search in Scopus of the term food science and AFM yields 230 publications since 1991, whereas AFM in biology, for example, AFM and lipids, yields 7,000 publications. A few examples of the applicability of AFM can be seen in the following slides, where we have imaging of E. coli, correlated structural and mechanical changes of oral lipids in milk pulp membrane, characterization of polysaccharides, protein and toxin detection in food, mechanical properties of fluids, etc. In the next slide, we can see casein in milk at different pH environment. So what is the future? Well, a major limitation is that there is no direct identification of components in complex systems. Food is composed of many building blocks. However, coupled with high-resolution spectroscopy techniques, for example, coupling FM with Raman or with cyclotron radiation, can give further insight and further information regarding food processes. Experimental techniques can be improved, redesigned, and this can give rise to a new discipline called condensed matter physics in food science. Thank you for your talk. Thank you for your time.